Hello, my dear students. I welcome you all in this first lecture on the course of Operations Research. In this lecture, at first, I will briefly introduce the topic of Operations Research or Operational Research. Once the introduction of OR will be given, then later we will get into the topic of the standard and canonical form of linear programming problems. In order to solve a linear programming problem, we need a very fundamental concept that is called the idea of basic feasible solution, which also will be discussed in this lecture. We note that I have mentioned this is a course on operations research, or this operations research. This word is American English, and when we refer British or Europeans, then in that case same operations research is known as operational research, but both are often shortened to just the term OR. For this OR, the British use operational research, and US use is operations research. And another term which is used for the field, this operations research, is the management science, or it is also abbreviated as MS, management science. The Americans sometimes combine the terms OR and MS together, and they usually refer it as OR or MS, or just they combined, and they also refer this course, this operations research, as ORMS. Yet another, yet other terms sometimes are used. Those are industrial engineering and decision science. However, in recent years, there has been a move towards a standardization upon a single term for this field, and it is named uh, is the just simple term OR. Operations research, is a relatively new discipline. The content and the boundaries of OR are not yet fixed. Therefore, to give a formal definition of the terminology operations research is really difficult task. If you just Google what is operations research, you will find that several definitions are given, and no definition uniquely identifies the task of operations research. And therefore, it is really difficult task to give just one unique definition of the terminology operations research. The OR starts when mathematical and quantitative techniques are used to substantiate the decision being taken. So, as and when you are trying to solve some decision making problem, there the application of mathematical and quantitative techniques from anywhere, in the sense of you can bring certain topics from statistics, you can bring certain uh, mm, ideas from control theory, you can bring certain ideas from industrial engineering, you can bring certain mathematical tools to solve your decision making problem. All these ideas to solve decision making problems are just clubbed together, and they are given the terminology operations research. In our daily life, we know that we simply, by common senses, we take decisions, we take judgment, um, just by applying our simple common senses without using any mathematical or any other model in simple situations. But you note that when we need to take some decisions in a very complex situation, for instance, you consider public transportation network planning in a city having its own layout of factories, or residential blocks, or finding the appropriate product mix when there exists a large number of products with different profit contributions and production requirements, etc. You note that in such situation, just by common senses, you will not be able to handle the decision making problem. You will not be able to find an appropriate optimum decision for such complex situations, complex network problem or production planning problem, or product mix problems, inventory problems, transportation problems. Those are certain complex situations where common senses will not work, and they are thus the need of studying the model problems to solve such complex problems. And this is the essential task of the topic of operations research. And as I mentioned, operations research tools are not from any one discipline. Operations research takes tools from different disciplines such as mathematics, statistics, economics, control theory, several engineering fields, even psychology, all these things. And all these things are combined, and these are combined to make a new set of knowledge for decision making. And today war became a professional discipline which deals with the application of scientific methods for making decisions, and especially to the allocation of scarce resources. The main purpose of OR is to provide a rational basis for decision making in the absence of complete information, because the systems composed of human, machine, and procedure may do not have complete information. Operations research can also be treated as science in the sense of it describes, or it is used in describing, understanding, and predicting the system behavior, especially when this today's era of machine learning, where man machine system, we are all chasing about man machine system or machine learning. In today's era, operations research can be thought of as science. And obviously operations research is not a mathematical, or not just only um, it just coming from the one field mathematics. It is not a sub branch of mathematics. The terminology operations research, it flourished possibly after the development of simplex method for solving the linear programming problems, which is usually shorthanded by LPP, linear programming problem. The terminology operations research, it it was around 1940s, or more precisely 1945 to 50s. During that time, George Danzig, one US mathematician, who developed the simplex method to solve the linear programming problem. Simplex method was developed by US mathematician George Bernard Danzig. And soon after the development of simplex method to solve linear programming problem, Several management scientists started extensively applying it in solving management science problems or several critical decision making problems. As management scientists were not very involved with mathematical tools of the simplex method, they started calling all the methods to solve decision making problems as a whole by operations research. And since then the terminology pertained, and people started calling all the methods to solve decision making problems as just one terminology, OR, operations research, as if several operations are being applied, several critical operations rather, they are being applied to solve a complex decision making problem, and thus the terminology operations research. However, from where exactly the terminology operations research started is not neatly traced yet. Okay, and George Janji is not the one person who developed the simplex method. Obviously, he was the person who started talking about solving in a systematic manner the linear programming problems. However, almost at the same time, Kantorovich, who was Russian, one Russian mathematician, Leonid Kantorovich, also came up with the mathematical technique which is now known as linear programming, and possibly in 1930s, precisely 1939, Kantorovich also was found the topic of linear programming problem, and it was just some year later, Kantorovich Danzig developed the systematic procedure to solve the linear programming problem, that is the simplex method. Leonid Kantorovich worked for the Soviet government, and he was given the task of optimizing production in a plywood industry, from where he was known for his theory and development of techniques for the optimal allocation of resources. He is regarded as the founder of linear programming, Kantorovich, and he was the winner of the Stalin Prize in 1949, which is a very famous prize. Possibly I'm not wrong with the spelling. Stalin Prize in the year of it was 1949. Sorry, may not be this E will not be there. Stalin Prize in 1949, and also most reward, the Nobel Memorial Prize in Economics was also given to Kantorovich in 1975. Nobel Prize. Nobel Memorial Prize in Economic Sciences, obviously not in mathematics. Nobel Prize is not given in the field of mathematics. However, if you work on optimization, if you work on operations research, and if you develop certain um, novel idea which breaks all the ideas of, which breaks means I mean if it is a path breaking work in operations research, then you also will be able to get the Nobel Prize, and obviously not from mathematics, not being a mathematics student, but you will be treated in that case as economist or economic sciences. And it was happened to 1975, where Nobel Prize was given to Kantorovich, and it was not just only one person. In 1975 Nobel Prize was given, and this Nobel Prize was given jointly with one Dutch American mathematician, Koopmans, T.C. Koopman, Jalling Charles Koopman. in 1975, this Nobel Prize was jointly given to Kantorovich and T.C. Koopman for their contributions in the field of resource allocation, especially for the theory of optimal use of resources, which is obviously a topic of operations research. And you know, when I was talking about this foundation of linear programming problem, and usually Danzig, the US mathematician Danzig, is usually thought of as the father of the simplex method, but it is not really so. George Danzig and Kantorovich, they together are thought of the pioneer of the linear programming problem. Although this terminology linear programming is not given by Kantorovich, neither by Danzig. This terminology linear programming was given by Koopman, and sorry, it is not Koopman, it's Koopman's. So I'll tell you the story how this linear programming terminology coined up. George Danzig was recruited during the Second World War in U.S. Army. He worked for U.S. Army, and the military refer to their various plans or proposed schedules of training, logical supply, and development of combat units. They all refer all these things: planning, scheduling, or logical supply and development of combat units. All these things are they together called it as a program. Like we all in our common day-to-day use of the English terminology program. For instance, if there is a schedule of events, we say what is the program of the events. So this scheduling of training, this task was given to Danzig to find an effective scheduling. And Danzig was the first person who analyzed the Air Force planning problem and saw that it could be formulated as a system of linear inequalities. And thus, he called his first scientific article as Programming in a Linear Structure. Programming in a linear structure. This was the title of the paper by George Danzig in 1947. And soon after the development of his idea of programming in a linear structure, and this terminology, this programming is referred as the scheduling problem, which was given to Danzig to solve by the US military during the Second World War. And in 1947, George Danzig wrote this paper, Programming in a Linear Structure, where he has used the geometry of column space of a matrix to solve a linear programming problem. And that was the idea of the simplex method. I will describe all these things in detail. You know that when he wrote his paper Programming in a Linear Structure, then afterwards he gave a talk in the Zero Symposium of Mathematical Programming in Berkeley. And there was several discussion about this programming a linear structure. And in 1948, Rand Corporation in Santa Monica, United States, they called George Danzig as an expert on solving linear programming problem. In 1948, it was Danzig visited the Rand Corporation, and one day during his visits, um, he took a walk near the Santa Monica beach with uh, his friend Koopmans. He described all his method in a verbal language, and after hearing all this conversation, Koopman said, "Why do not you shorten programming a linear structure to just linear programming?" So it was Koopman who has suggested the terminology all this entire topic, programming linear structure, as linear programming. And this word programming is not related to the computer programming that we all know today. By programming, when we call some coding classes, we call C programming, C++ programming, Java programming and all. So this word programming is nothing to do with the computer programming, computer coding. This programming terminology came from the word scheduling. Fine. Uh, and since then, and it was 1948 when George Danzig and Koopman they visited Rand Corporation, which is a very famous corporation for computational tasks. And this Rand Corporation, once they visited in 1948, Koopman suggested the terminology linear programming, and since then the terminology um, linear programming pertains, and people refers programming in a linear structure as linear programming. As LPP, or the linear programming problem, is the basis for the development of solution algorithms of other more complex types of operations research models, including integer programming, nonlinear programming, or stochastic programming. As LPP is the basis for development of all these topics, mathematical topics, we endeavor to learn deeply the core topics of LPP with greater mathematical rigor in this course. To note that study of LPP is a part of the mathematical topic called optimization. Optimization is also many a times equivalently referred as nonlinear programming. And optimization theories are mainly product of the interplay between calculus and geometry. The field of optimization is concerned with the study of maximization or minimization of mathematical functions. Very often, the arguments of the objective function, that is the variable of the function, are subjected to some constraints, or these are called as side conditions. For instance, in your mathematics 1 at IIT BHU, you have learned the Lagrange's multiplier rule to solve this particular maximization or minimization problem, that maximize the function fx subject to some equality constraints. G1x is equal to b1, g2x is equal to b2, with maybe there may be some other equality constraints as well. So you all have learned in your mathematics 1 course the Lagrange's multiplier rule to solve such problems, and these problems are called as maximization problem, or broadly under the umbrella of optimization problem. And these arguments, the here this function fx is referred as the objective function, and the argument or the variable of the objective function is known as the decision variable. And these variables are restricted by these inequalities, right? And the collection of the decision variable points, that means the collection of x's for which u1x equals to b1 and g2x equals to b2, is known as the decision feasible region. That means you have to maximize this objective function fx subject to x lying in the set, in this set x lies, small x lies inside this set of all x's, such that gix is equal to bi. For I equal to, we have here two equality constraints. Fine. This set capital X is called as the constraint set. Why constraint? Because you know that you have to optimize or maximize this objective function fx subject to x satisfying these conditions, right? It is not that x is unrestricted to lie in the entire n-dimensional space. As x has to lie, you have to optimize this function fx provided that the variable x is lying inside this set. So there is this particular restriction. Satisfying this restriction, you need to optimize or maximize this objective function. That's why this set capital X is called as the constraint of the problem. And by virtue of great utility of the optimization theory in diverse areas of applied sciences, engineering, economics, finance, medicine, statistics, due to several diverse application of this optimization toolbox, optimization holds an important place in the practical world and the scientific world. Indeed, as far back as the 18th century, the famous Swiss mathematician and great physicist Leonhard Euler, who proclaimed that nothing at all takes place in the universe in which some rule of maximum or minimum does not appear. I repeat what Euler said. He mentioned nothing at all take place in the universe in which some rule of maximum or minimum does not appear. Nothing is there in the world without maximum or minimum. You know that in our day-to-day life we keep on using the terminologies optimize, minimize or maximize. You want to invest less, you want to get profit maximum. So with just this simple idea, you know that at every day, at every step of our life, we require the knowledge of optimization. Before embarking the journey of joy, learning the mathematics of linear programming problem, or which is a subpart of optimization theory, let me mention a few application areas of linear programming problem. The application of linear programming problem, although will not be talked in this class in detail, if we get some time, then we will get into the transportation problem and assignment problem. At most, we may catch some network problem. Otherwise, we will not have much time to have at least a mathematical flavor of the basic understanding of linear programming. If we find time, then only I will get into these applications. Otherwise, this entire course will be just a mathematical description of the linear programming problem and its extension, or rather its application in solving simple game theoretic problem. To mention a few, application areas of operations research are accounting, construction problems, facility planning, purchasing, finance, manufacturing, marketing, organizational behavior or human resources. Let me give you a few examples of accounting, like assigning audit terms effectively, credit policy analysis, cash flow planning, developing standard costs, establishing costs of byproducts. These are all topics of accounting. In construction, for instance, you consider project scheduling, monitoring and control, determination of proper workforce, deployment of workforce, allocation of resource to projects. These are few topics of construction. Few topics of facility planning are factory location and size decision, estimation of number of facilities required, hospital planning. These are few applications of few topics of facility planning. few more are factory location and few more are like international logistic system design, transportational load and unloading. Few topics of purchasing are optimal buying, optimal reordering, material transfer, etc. Few topics of research and development are R&D project control, R&D budget allocation, planning of product introduction. Few topics of finance are building cash management models, allocating capital among various alternatives, building financial planning models, investment analysis, portfolio analysis, etc. Few topics of manufacturing are inventory control, marketing balance projection, production scheduling, production smoothing. Few topics of marketing are advertising budget allocation, product introduction timing, selection of product mix, deciding most effective packaging alternative, etc. So these are just few applications of operations research or applications of linear programming problems. Um, with these few words, this very few introduction of operations research, let me tell you what is the task of the entire course mathematically. Mathematically, in this course, we will try to learn effective ways to solve a linear programming problem, which is to find maximum or minimum value of a linear function subject to linear equalities, where here C is a constant vector and it is one n-dimensional vector. The variable here x is having n many components. The matrix capital A is a matrix of order m by n, and the vector B is a vector of m dimension. In this course, any vector, for instance, here we have used the vectors x, we have used the vector c, we have used the vector b. Any vector in this course will be represented by a column vector. Here x is having n components, so x will have explicit form as x1, x2 as the second component, xn as the nth component. Similarly, for the vector c, which is a constant given vector, it has this form: c1 as the first component, c2 as the second component, and cn as the nth component. The vector b is an m-dimensional vector. It will thus have m many components. First component is b1, second component is b2, and the mth component is bm. The matrix A, capital A, as it is of m by n dimension, therefore it will precisely have n many columns, m many rows. If we represent the columns of the matrix A by A1 as the first column, A2 as the second column, An as the nth column, then we note that this vector A1 is nothing but this column vector, that A11 is the first component, A21 is the second component, similarly AN1, sorry, it has m many components, so AM1 as the mth component. Similarly, the vector A2 is having the first component as A12, then A22, then it has AM2 as the mth component, and at the last the vector AN is this column vector A1n, A2n, and till the nth component is AMN, and therefore explicitly this LPP can be presented by, which is equivalently presented by maximization of C1x1 plus C2x2 plus till Cnxn subject to A1x1 plus A2x2 plus Anxn is equal to B. You can further explicitly present here just by, here you note that inside of this constraint you have m many components. Those all you can explicitly write. This is the vectorial form. This is the matrix form. Ax equals to b. A is the matrix, and here this is called the vectorial form of the constraint set, that Ax equals to b. Here there are few terminologies. Those terminologies are as follows. The function C transpose X is known as the objective function. C transpose X, which is obviously a linear function, and it is known as the objective function. Here we note that this maximization process or this maximization problem is asking you to find the maximum most value of C transpose X subject to your X is satisfying this condition that X equals to B, and thus this X equals to B is known as the constraint of the problem, and it is known as the constraint set. Constraint set or the feasible region. It is the set, it is the collection of all points in the n-dimensional Euclidean space subject to this X is satisfying all the m equalities inside of this Ax equals to B. You note that here this maximization problem or this optimization problem is a problem where the objective function is a linear function and the constraints are given by the linear functions. What are those linear functions? Here you note that inside of Ax equal to B, the left hand side has this Ax equals to B. On the left, this Ax equals to B, if you try to write it explicitly, it has precisely m many components, right? The first row is a11x1 plus a12x2 plus till plus a1nxn, right? This is your first component of Ax. The second component of Ax is a21x1 plus a22x2 plus a2nxn, and the mth component can similarly be written by just replacing this 2 here in the second equation by m. Fine. And these such functions, you note that this function, the component, first component is a linear function. Linear function of the variable x. Here also this is also a linear function of the variable x. And thus this problem is asking you to find maximum value of a linear function subject to linear equalities, and thus the nomenclature linear programming problem. The terminology linear comes from the fact that here all the functions those are involved in your optimization, in your maximization problem, here all the functions are linear, and that's why the terminology linear programming problem. Here you note that here I have just mentioned only one particular linear programming problem. However, the general form of a linear programming problem is of this type. General form can involve this. Instead of ax equal to b, generally you will have ax less than equals to b. You may have some more constraint here. Instead of x belonging to the entire n-dimensional space here, you may put some side constraints. Those are x greater than equals to 0. That means you wanted your variable values are all lying in the first quadrant or first octant of the n-dimensional Euclidean space. Fine. That means here x greater than 0, it signifies all the components of the variable x are all non-negative. Fine. So this is usually thought of the general form. Here you may have certain possibilities, like few components of x's are greater than equals to zeros, few other components are unrestricted in sign. So there can be several varieties of the general linear programming problem. In order to develop theories for solving general linear programming problem, usually we standardize a given problem into a very specific form of the linear programming problem, and that is called the standard linear programming problem. So here in the next, let me tell you two special forms of linear programming problem. Those are called as the canonical form or the natural form or the usual form of the linear programming problems, and another is the standard form. And standard form will be extensively used in developing general theory of linear programming problem. Fine. The canonical form of the linear programming problem is the following. Canonical form of linear programming problem. The terminology canonical refers to usual or natural form of, or usual natural. These terminologies are equivalent to canonical, and that's why the terminology canonical form of an LPP. It is this problem: maximization of C transpose X subject to, it is not such that, it is subject to Ax less than equals to B together with x greater than equals to 0. This is called as the canonical form, where in the entire course, unless otherwise specified, we will mean here in this problem statement this vector C is a given constant vector and n-dimensional vector. That means the C that I have written here, that this C will be considered as the general C. As in when I am just writing C transpose will mean that C is this n-dimensional constant column vector. Similarly, this B is this m-dimensional column vector, and capital A is m by n matrix, where a1, a2, an are the column vectors of the matrix A, and x is of n dimensional vector. So x will have n many components. Fine. Here you note that in the canonical form we need three conditions. At first is this condition that the problem should be in maximization form. This is the first condition, that you need to have the problem maximization problem. You may ask the following question during the discussion of the linear programming problem. When I started with maximization, some of you might have already thought, why am I considering maximization? You may also equally consider here minimization. There is no problem at all. However, in order to develop theories which will be applicable to general problems, obviously we have to take a standard problem and then develop theories. And once the theory is being developed for a standard problem, then you get back to, from the standard problem you get back to your given problem and you apply the result of the theory, and that is how the process will be. And we note that taking maximization is not a loss of any generality. because of the fact if it is a minimization problem, suppose it is a minimization problem, then you note that minimization of C transpose X is nothing but maximization of minus C transpose X, right? Or if you wanted equal values on both the sides, then it will be negative or maximum of negative of C transpose X is nothing but minimum of C transpose X. So if you have a minimization problem, you can equivalently pose it as a maximization problem just by placing a minus C here, minus C transpose X, fine. And therefore there is no loss of generality if we are considering to discuss or develop theories only for maximization type problem. And in canonical form, we assume that the problem must be given in the maximum form, maximization form, and obviously this is not a standard condition, although we can write also it is a minimum, but let us agree with, in this course let us agree with the canonical form, that as and when we are considering canonical form, then we will have only maximization problem. So this is the first condition. Second condition is that you should have less than equals to sign here, ax less than equal to b. And the third condition is that you should have the non-negativity restriction of the variable. So if these three conditions are being satisfied in the statement of your problem, that problem is called as in the canonical form. Fine. So this is your canonical form, and by the standard form we mean the following. The standard form of linear programming problems is that it is of this form, that it is a maximization problem C transpose X subject to Ax equal to B together with X greater than equals to 0. Here we have a restriction on B, that this restriction is that these B vector must have all the components greater than equals to 0. Fine. So in the standard form of an LPP, we have four specific conditions. The first condition is that the problem must be in the maximization form. The constraint are all equalities. The constraint are all equalities except the non-negativity restriction of the variables. Here the third condition is that this this B vector is usually referred as the requirement vector. Why requirement vector? Because in the management science, you know, requirement vector, you know, it is usually in management science or finance problem, usually it is thought of that the objective function is the cost function, which you, or profit function if it is a maximization problem. So this objective function is usually the profit function, and here ax equals to b is some kind of mathematical representation of the resource allocation. That means you have certain amount of resources, and those resources should meet some requirement, and those requirement values are placed on the right hand side of the constraint set, and that's why this b vector is called as the requirement vector. And here I make a special note here, that make a note, let me take different color, note that maximization of C transpose X is equal to negative of minimization of minus C transpose X, or vice versa, that minimization of C transpose X is my negative of the maximization of minus C transpose X. So if the problem is given in the minimization form, you can equivalently place it as maximization form. And so these are two particular forms of linear programming problems, and these particular form, the standard form, will be extensively used. Not only extensively, this is the only form of linear programming problem which we will use in the description, in the derivation of the entire theory on solving linear programming problems. And therefore I need to mention a few standardization process that given any general linear programming problem, how can we standardize the given linear programming problem? For instance, if the problem is given in this usual form or in the canonical form, then we know that in the canonical form already two restrictions are being satisfied. The first restriction is it is in the maximization problem, greater than equals to. So out of the four conditions, here it is the fourth condition. Out of the four conditions of the standard form of the linear programming problem, canonical form is already satisfying two restrictions. That the first restriction is this maximization, and the fourth restriction is this x greater than equals to 0. These two restrictions of the standard form are already being satisfied by the canonical form. So in order to reformulate the canonical form into the standard form, what we need to do is we have to make these inequalities as equalities, and also we have to make the right hand side vector b as that all the components of b are non-negative. Fine. So that will make the any canonical form into the standard form. So let me just consider a few standardization operation, and with the help of that I will mention the standardization operations. With the help of them we will be able to find we will be able to convert any given linear programming problem into the standard form, and therefore any given linear programming problem can equivalently placed as a standard form into the standard form, and thus there is no loss of generality if we develop theories of linear programming problem only for the standard form of linear programming problems. Fine. A few standardization process are as follows. First one is, we note that if the problem is a linear programming problem, then obviously the objective function is always in the linear form. We don't have to worry about it. So what are the possibilities for not satisfying the requirement of the standard form? So those possible points are as follows. The problem may be in minimization problem, which can be easily placed by maximization problem just by placing a negative sign in the objective function, right? So that is just a left hand job. But you may have certain restrictions which are in the form of inequalities. For instance, you may have, for instance, let's suppose you have 2x1 plus 3x2 less than equals to 5. This is a possible constraint of a linear programming problem, because on the left hand side you have one linear function and therefore it is a linear inequality. Now how do we make this linear inequality as a linear equality? Because you need equality here in the standard form, and here it is usual that the left hand side 2x1 plus 3x2 may be less than strictly, or maybe it is equal to 5. So in order to make here it is equal to, what we need to do is we have to add certain amount of value. Let's suppose another value x3, where x3 is a non-negative uh, quantity. So if you add this deficit value to reach the value 5, this x3 if you add, let's suppose I have certain value of x1 and x2. Let's suppose I have x1 is 1 and x2 is your for x1 is equal to 1, x2 is equal to, let's suppose, 0. We know that how much amount is deficit to reach at the value 5, 3, right? So we assign the value x3 to x3 as the amount 3, and then we note that you will have equality here, equal to 5. So similarly, just by varying the values of x1 and x2, you consider this x3 to be added, um, and this value or this amount x3 which is just added to the left hand side to make it is equal, as if there is a slack quantity on the left hand side, and that slack quantity is x3. Once it is added, it will reach to the value 5, and that's why this variable x3 is called as the deficit variable or the slack variable. So just by adding a slack variable x3, you can make this inequality restriction to an equality restriction. So this is called as adding slack variable. Similarly, you might have instead of here less than equals to, you might have here greater than equals to sign. In that case, what we need to do is you need to subtract a quantity which is excess, and that excess quantity is, let's suppose, x4, and this x4, once you subtract, you will reach up to 5. This x4 variable is again restricted by x4 greater than equals to 0, then only equality to 5 can happen, and thus it is called as if excess variable or surplus variable. So adding slack variable, adding slack, or subtracting surplus variable. Surplus variable, sorry. And this operation is some kind of, let's suppose, let me write it out for a general inequality. For instance, let me suppose I have the pth inequality in the constraint. Here you know that you have how many inequalities in ax less than equals to b. You have m many inequalities, right? So let's suppose the general inequality is the pth inequality. So if the pth inequality, if I consider, and let's suppose it is of this form, p1 x1 plus a p2 x2 plus a pn xn is equal to bp. This is your pth inequality, and inequality, sorry, I placed here equality less than equals to bp. So here you need to add a slack variable, which is your, if I add just a slack variable, let's suppose that variable is sp is equal to bp, where sp obviously is greater than equals to 0. A p1 x1 plus a p2 x2 plus a pnxn, you add this deficit quantity sp, and this is called as the slack variable or deficit variable or the shortage variable. This is called as slack variable. You may have the pth inequality, or let me suppose the qth, a q1 x1 plus a q2 x2 plus AQNXN is greater than equals to BQ, the qth inequality of the given problem. And this can be equivalently written as a q1x1 plus a q2x2 plus a qnxn minus the surplus variable sq is equal to bq, where sq is a variable greater than equals to 0, and this variable is called as surplus variable. So just by adding a slack variable or subtracting a surplus variable, you will be able to convert one inequality restriction to an equality restriction, which you require in the standard form. In the standard form, all the restrictions are to be in the equality form. Fine. You may have some possibilities of the variables here, this 2x1 plus 3x2. Here, some of the variables may be unrestricted in sign, right? Maybe you have x1 greater than equals to 0, but x2 is unrestricted in sign. In that case, what we can do is, you know that in the standard form, you need to have all the components of the variables non-negative, right? And therefore, if one or more variables are unrestricted in sign, we have to place that particular variable uh, somehow, that variable must be containing non-negativity restriction. How can we do that? And for that, we know that if, let's suppose, my pth variable xp is unrestricted in sign, that means xp can take positive value, xp can take 0, xp can take negative value. Such variables can be written as difference between two non-negative variables xp and xp double dash. For instance, let me suppose I have the value 3, and this value 3, you know that you can write it as 4 minus 1. If xp takes the value 3, a positive value, I am giving one instance of positive value. If xp takes a negative value, then also you know that we can write it as difference between two positive values, 4 minus 5. Fine. And therefore, here I have just written 4 minus 5, you could write here 2 minus 3 in several other ways. And therefore, we note that any positive or negative variable can be written as difference between difference between two non-negative variables, right? So here, just by introducing one more variable xp, you had in just replace the xp by two more variables xp dash and xp double dash, and where xp dash is greater than equals to 0, as well xp double dash is greater than equals to 0. Just by introducing two more variables, you can get the problem where the problem will not have the variable xp. The problem will have xp dash and xp double dash, and with the variables xp dash and xp double dash, obviously your problem satisfies the non-negativity restriction of all the variables, right? I'll give one example so that this idea will be much more neat to you. So if some variables are unrestricted in sign, in that case you introduce two non-negative variables and you take the difference of them, you will resolve the issue of unrestricted sign variable from the problem. You may have some inequalities which are given in the absolute form. For instance, For instance, you may have, let me consider a very specific example of two variables. Let's suppose I have a11x1 plus a12x2 less than equals to b1. We note that this can be equivalently written as a11x1 plus a12x2 less than equals to b1 as well. Together with this less than equals to b1, so this and a11x1 plus a12x2 is greater than equals to minus b1, right? And from here you add two variables that you add here is slack variable. So here a11x1 plus a12x2 plus x3. x3 is a slack variable here. x3 is equal to b1, and here a11x1 plus a12x2 plus, sorry, minus x4 is equal to b minus b1. Fine. And therefore now you have resolved the issue of absolute form of inequalities. If we have some inequality like this, then we know that this can be equivalently placed by two equalities. These are these two. Fine. And you note that here you may ask the following question, that we could take the absolute form inequality as, instead of less than equals to, we could possibly take greater than equals to b1. And in this case you may feel this is a possible inequality in a linear programming problem, but we note that unless b1 is 0, this region, that means the set of all values x1 x2, for which absolute value of a11 x1 plus a12 x2 is greater than equals to some non-zero value b1. Obviously b1 has to be positive, so a positive value b1 may be a possible constraint in a linear programming problem, but this is not really so. This is due to the fact that if I try to draw out the regions for this greater than equals to b1, so what you will have is this is the line for, let's suppose, equal to b1, and then this will be the line for equal to minus b1. They will be parallel in sign, and for one inequality you will have less than here this side, another inequality will be of this side. You can just take an example so that you will be able to sense it. For instance, let me just simply consider one example. For instance, you please draw this, you please try to find out this region greater than equals to 1, and then you will be finding that this is the region. That means this set is a null set, this set is an empty set, right? And once this empty set is there, obviously once this set is empty, then your problem is not well defined, that you want to maximize the objective function subject to an empty set. Fine. And therefore this problem is just a vacuum, right? And therefore this restriction greater than equals to, this is greater than equals to with the absolute form, will not be there, will not be a possible inequality in a linear programming problem. Fine. Now let me consider one example on standardizing or placing a given problem in a standard form, so that the idea will be clear to you. The operations, those I have mentioned, the three operations, Let me consider the following example. Put the following LPP in standard form. Here, let me explicitly say one thing that I'm missing here. You know that when you have this greater than equal to 1, in this case it will be, let me explicitly say, it will be not precisely just the empty set, because here this is not in the AND form that it will satisfy this side and this side. It will be of this form. Explicitly, if I want to write, then it will be x1 plus x2 is greater than equals to 1, or this or, unlike here and we had for less than equals to b1, we had and here, but for greater than equals to 1 you will have or x1 plus x2 is less than equals to minus 1. Then you know that your region of restriction will be either this or this, and this region, this red region, which represents this inequality, this red region, this red region, this side or this side, is your set of points which are satisfying this inequality, that modulus of x1 plus x2 greater than equals to 1. And this shaded region is not a convex set, and once it is not a convex set, this cannot be a possible inequality in a linear programming problem. And that's why in no way this will be a possible restriction in a linear programming problem. Fine. Now let us try to put the following LPP in the standard form. The given problem is the following. Minimize the objective function z equals to 3x1 plus x2 plus 2x3, subject to minus 2x1 plus 4x3 is equal to 3, the first restriction. Second is x1 plus 2x2 plus x3 greater than equals to 5, and you have modulus of 2x1 modulus of 2x1 plus 5x3 less than equals to 2. You have x1 greater than equals to 0, x2 also greater than equals to 0, but x3 is unrestricted in sign. Fine, so this is your problem. Let us try to place it in the standard form. To place it in the standard form, you know that what we need to have here, that all the restrictions, all the variables are to be non-negative in sign. Also on the right hand side, all the values are to be non-negative, that means the b vector. As well, these restrictions are also to be in the equality form. The first restriction is okay with us, that first restriction is in the equality form which we wanted for the standard form. In the second inequality, so let me just write the first inequality, 2x1 plus 4x3 as it is, 4x3 is equal to 3. Then for the second inequality, we need to subtract one surplus variable, x1 plus 2x2 plus x3 minus x4 is equal to 5. Once you are introducing a surplus variable x4, therefore you should have this x4 greater than equals to sign 0, and for this inequality, that absolute of 2x1 plus 5x3 less than equals to 2, this is equivalent of two inequalities. The first one is 2x1 plus 5x3 is less than equals to 2. For less than equals to 2, I add a surplus variable is equal to 2. I add a slack variable x5, so here x5 is greater than equal to 0. And we also have uh, that from this absolute inequality, you also have 2x1 plus 5x3 is greater than equals to minus 2, right? So let me just simply make a side calculation that the next inequality is 2x1 plus 5x3 is greater than equals to minus 2, right? So we need to subtract a surplus variable x6. So I put here x6 greater than equals to 0, and once I am subtracting the surplus variable x6, we need to have here equal to sign, but here note that once we have in the equality form, on the right hand side you have a negative component, so we multiply minus 1 on both the sides, and you will get minus 2x1, then you will have here minus 5x3 and plus x6 is equal to plus 2. Fine. And what else is there? You know that here the variables x1, x2 all are non-negative in sign, all are non-negative. x1, x2, these are x1 is greater than equals to 0, x2 is greater than equals to 0, x4, x5, x6 are all greater than equals to 0s, but x3 is unrestricted in sign. So for x3 we need to introduce two variables, that x3 dash minus x3 double dash. So here this x3 will be x3 dash minus x3 double dash, and this x3 also x3 dash minus x3 double dash. Here also this x3 is x3 dash minus x3 double dash, right? And then we have x3 dash greater than equals to 0, x3 double dash also greater than equals to 0, and this is your standard form. These are all any restrictions, and you have here minimization problem. So let me put it in maximization problem. For maximization, you will have maximization of minus z. It will be minus 3x1 minus x2 minus 2x3. But for x3, we have here x3 dash minus x3 double dash. So this is your standard form. Standard form is this one. Right? So this is how we will standardize. So for any given linear programming problem, you can effectively make it in the standard form with the use of these three operations, that adding or subtracting slack or surplus variables respectively, or if some variables are unrestricted in sign, then you introduce two variables, take their difference and get a resolved um, get a resolution of the issue of unrestricted in sign, and also this absolute form inequality can be converted into two equalities. Fine. This is how the standard form will look like. Now let me end the today's class here. On the next lecture we will start looking at how we will proceed solving a given standard linear programming problem. Where to start with, we know that in the standard form you need to maximize the objective function subject to ax equals to b, where x is greater than equals to 0. Now here x is greater than equals to 0 is nothing to do with by that I mean it is just a restriction of the variables. But here the major task is to solve effectively this x equals to b. Then only you will be effectively able to find, effectively you will be able to reach at the optimum solution of the given problem. So we will see on the next day that just by effectively visiting a few points of the solution set of x equals to b, you will be able to reach at the optimum solution. So the next day we'll start with a very simple graphical perspective of the method, and then we will rigorously develop the mathematics behind it. This entire course, in this entire course, I would always like to go with common intuition. That means the description always before the description of the theories or methodologies. At first, I will try to look at the problem geometrically in a simple two-dimensional case. And once we have a sense of how we can proceed towards reaching at the optimum solution, once the sense is clear, then the development of the theory will be much more easy before us. And therefore, at first, on the next day, I will start giving the idea of the simplest method geometrically, and where we will find that we will require the notion of basic feasible solutions. And basic feasible solutions are nothing but the possible candidates of the optimum solution. Although theoretically we will prove the fundamental theorem of linear programming problem, which says that if there exists one optimum solution of the problem, it must be obtained at a basic feasible solution. Fine. We'll prove this result, and thus the notion of basic feasible solution is very, very important in the study of linear programming problem. On the next day, I will start with the idea of basic feasible solution, then we will proceed with the systematic way to solve a linear programming problem. With this, I end here. I thank you all for all of your kind presence.